No problem. Please take a seat. Yeah, no problem.
Perfect. So appreciate everybody's time. Great to get introduced. What do you do, by the way? My name is Ben, by the way.
I'm Jacopo. I'm a founder of a company. I also talk here later on today.
Awesome. Well, great to get introduced. So, my background is more heavily suited within the physics world. So I did a lot of grad work in AMO, atomic molecular optical physics. I ended up, researching a lot of genetic learning algorithms back in the day. Specifically working on like simulations that facilitate qubits, things like that. I then jumped into the world of technology, right? So, walked through quite a few different talk tracks. Now, I'm more centered around data storage and how data storage impacts like life science workloads and things like that. So kind of give you my background and my perspective and things and why it's there. I work now for a company called Weka that does do data storage. So that's why this talk is going to be a bit centered around data storage and its impacts within AI and GPU environments. But feel free to stop, ask questions as we go. Thanks for being a part of the journey. So the world's been a very interesting place over the last couple of years. Specifically, the last 2 years have been incredibly interesting with NVIDIA's kind of meteoric rise. I personally started investing heavily within the GPU infrastructure when it comes to training models and things like that, probably around like the 2012 era, back when CUDA was first being developed and you had to parallelize your code, and it was an absolute nightmare, right? Since it's changed. And what's been interesting is you've started to see a subset of folks going from MPI workloads, which is massive parallel CPU-based workloads, to GPU-oriented workloads for AI simulations. And GPUs have kind of changed the game from a compute perspective, right? No more are you dealing with 32, 64, 128 core procs and a CPU, and you're trying to process kind of linearly in an MPI-like format if you're doing massive scale HPC or just generically. Now you're using GPU acceleration, right? You're having tens of thousands, the millions, the billions, trillions of cores and transistors within a single system. It's enabling a different type of computing technology out there that is kind of changing the game. We've also seen a crazy change within networking, right? And again, part of the NVIDIA Mellanox acquisition a long time ago was moving us from 1 gigabit, 10 gigabits in the past to 400 and 800 coming out soon. And it's kind of changed the networking ability to really feed large data pipelines to these GPU-based systems, which can do this incredible type of computing. Now, the problem is all of this is based off of what I'll call vintage storage, right? NFS solutions and things like that have historically been used for these types of workloads, but they're based on like 20-year-old basically technology that hasn't really evolved too much. Yeah, you have PNFS, you have various different types of additives to it that help increase the amount that a single NFS system can provide to a single GPU system. But in general, right, you need to really change the way that you're addressing your storage in order to optimize for the end-to-end infrastructure. So I like to think of everything below the middleware and application layer as kind of like a triangle, and you need to have a solid base across all three. And why everybody's been hyper-focused on GPU use and GPU consumption, networking, and making sure that networking centered, the storage aspect's been generically left alone, and it's causing for inadequacies within the performance profile of what you're actually putting out when it comes to any AI or GPU related workload within the cloud or on premise. So making sure that you're optimizing across that type of triangle is beneficial, not just to make sure that you can store data, but making sure that you're optimizing your algorithms and reducing your run times and reducing your overall operational costs associated with each independent run. And we'll talk to that in a bit. So I'm going to talk through this talk track, kind of talking through what I call impossible workloads that AI is helping to support. The first one's going to be more on the research and development phase, more so associated with life sciences. So life sciences have had an astronomical change within the last 5 years, right? You look at COVID and things like that, and vaccine creation, discovery, clinical validations, and it seems to be happening at a faster and faster pace, right? When you look at the time to market that Moderna and Pfizer put out their vaccines, it was somewhere around like a 6-month development cycle, and then it pushed into about a year and a half in order to get it out to us. A lot of that was pushed by regulatory changes within that industry, but what we're finding is drug development's happening quicker, right? You're having new types of drug development. You have small molecule science and things like that that are very heavily focused on being able to simulate what are the internal mechanisms for how these molecules are interacting with whatever pathogen or whatever type of protein might be creating some sort of like cancer or whatever it might be. But in general, right, you've seen a very fast increase in their discovery timelines. And why is that? A lot of times it's because of hybrid cloud use with burstable compute. So Moderna and Pfizer specifically, they were very interested when these things pop up. How can I be first to market? On premise, you can only have so much set infrastructure. You need to be able to burst when burst makes sense. It's like the conversation in retail, right? Black Friday, you see a massive spike for one day. You don't want to put on-premise infrastructure to be able to handle those spikes. You want to do your BAU business on premise and then be able to burst to the cloud. And this has created quite an interesting topology for them to differentiate. So few customers we work with that are referenceable, Moderna, 23andMe, customers that have taken the next step when it comes to pharmaceutical and clinical kind of discovery and process evolution. And a lot of times what they're doing is leveraging this type of hybrid cloud topology in order to do that. So you have some physical specimen, you're going to take that and push that through an Illumina sequencer or maybe a cryoscope in order to visualize what a molecule structure looks like. They then take that data set, they do a little bit of processing locally where that sample is being taken, just because you want to make sure that the image is good, right? So you don't have to repeat it before you're able to process it. And then they ship that out to the cloud. A lot of times it could be AWS, could be Azure, could be GCP, could be OCI. But a lot of times what happens is they'll push it out and then leverage expandable compute within the cloud in order to process that data. Now, the thing about expandable compute is you're sending this data storage out there, this data storage is sitting there, it's got to go into the compute. So you sit within some storage layer. And the storage layer really is an interesting piece, in my opinion, in order to optimize the end-to-end workflow. Because you need to have something that can facilitate a distributed model like this, right? Maybe you need a geo-distributed single namespace, maybe you don't. You need to be able to get the data out there. How are you doing that? Are you going to leverage a separate type of data mover tool? Are you going to leverage something internally? How are you going to be able to get a consistent environment across on-premise and in the public cloud? Those are difficult conversations. You have things like NetApp, for example, but NetApp isn't actually the same NetApp on-premise as it is in AWS, as it is in GCP, as it is in Azure, or as it is in OCI. It's a different variant. You have to custom create your code for it, and it causes a lot of problems in that scenario. So you need something that's going to be able to integrate with a hybrid cloud topology moving forward, and make sure that when you're thinking about what storage you're looking at for your AI workloads, that you're really thinking about hybrid topologies and how that makes sense. The other piece is in research and development, especially in the burstable compute segment, you really need to look at optimizing your storage to increase your performance and reduce your cost and time. The cloud charges per hour. It doesn't care what you're doing with that instance when you spin that thing up in AWS. OCI doesn't care when you spin up a bare metal shape. It's going to charge you regardless if you're using it or not. So when you look at how you can optimize your workloads, you need to not just look at the compute, you need to not just look at the network, you also need to look at the storage and what the storage can do. So recently I worked with a couple companies, one of those being Moderna, right? They're a referenceable customer, in order to look at drug development pipelines. So CryoSpark is a 14-step process, which basically creates a bunch of slices of a molecule, and basically allows you to visualize protein folds and things like that in order to understand, is there a molecule that I can stick in there that renders this particular protein fold inert, or do other types of simulations against it. So we basically looked at this and said, hey, we want to create some optimizations to figure out, does storage affect overall performance within the cloud, and how does it affect cost? So we took FSx Luster, which is a well-known file system within the public cloud within AWS for performance. And then my company, Weka. So I took Weka and I said, what's the difference between using just the same exact setup, same exact image, the same molecule image, the exact same compute images, and let's see what swapping the storage can do. So what we ended up seeing is that if you take a look at this chart to the left, this represents cost per run based on different types of GPU instances within the public cloud. And this is the Weka, and this is the FSx Luster. What we found is that your storage can affect your overall processing time for this type of CryoSpark system up to about 30 to 35%. And I dive in a little bit later into why that affects it. But in general, you can reduce your overall cost to make runs within the public cloud on GPU instances for your application just by making sure that you're optimizing the type of storage that you're on. Not even talking about what compute instance you're on, not talking about what your application's doing, just the storage can affect your overall run costs.
Can I ask a question?
Yeah. No, come
Just a clarification, where is the data in the cloud? Is it in S3?
So the data in this case in the cloud is using FSx for Luster. So these types of simulations and stitching together these images, think of like CryoSpark processes, taking a molecule, taking millions of image slices, and then doing center of mass calculations, stitching that together and creating a 3D model of a molecule that you're able to move. You can't use S3, you can, but you can't really use S3 for those types of processing because they require low latency, very fast type of computing topologies. In an S3 bucket within AWS, you're probably looking at capping around 3, maybe 4 gigabytes a second. You're also looking at latencies around the HTTP range, right? FSx Luster, for example, will give you latencies of around 750 microseconds to a millisecond. Right, it enables you to be able to access that over S3 versus or NFS versus S3, and it provides you with the ability to scale to 50 plus, 100 plus gigabytes a second. So this,
How much data can they support?
so the
And how much they cost compared to S3, which is like $0.00 per terabyte?
Yeah, so that's a great point. So when you look at a general file system in the cloud, it will cost more than S3, right? Some folks have started to use like S3 Fuse on top of an S3 bucket, but then your performance gets limited. So if you're trying to take a terabyte image, break that into a bunch of pieces, run compute against it and stitch it back together, you doing that through S3 actually will cause you more cost per run than it would doing that via a file system, because that file system performance is going to decrease your overall runtime, which you're going to get charged per run on the GPU, and basically take a look at it. So you need to make sure you're doing cost benefit analysis in whatever you're doing in the cloud. Does it make sense to run in EFS? Does it make sense to run in S3? Does it make sense for a file system? My file system, specifically Weka, it doesn't have any scale limitations within the cloud. It's basically a EC2, a bunch of EC2 instances, so it starts with 6 and it can expand out anymore. You deploy the software and user space on it, and then you attach it to an S3 bucket. So it has a small amount of performance based capacity. Let's say 5% is NVMe based, very fast performance. And then it stitches that across an S3 bucket, so you get S3 economics at scale. So it's a way of cost effectively storing data for a long period of time while providing you the performance of the file system. So that's really what I was pushing Moderna to take a look at. What's the difference between generic S3, and they would never use it there because it would never finish. What's the difference between a file system like FSx Luster, where you pay the exact same dollar per gigabyte per month, regardless of the size of the data set, regardless of how it's been accessed, anything like that. And then my file system that provides kind of a cache. I don't like calling that.
It's the cache. Yeah,
Function.
Yeah.
So we took a look at it, and again, it drastically affected per cost runs, right? So my point is, when you're looking at what am I going to do in these scenarios, make sure you're understanding how everything's stitched together. What is the storage you're using will eventually affect your bottom dollar cost, right? And there's a lot of options out there within AWS, within GCP, within Azure. So make sure that you're really thinking about that. And for Moderna specifically, it was less about like the overall cost per run, but more about how many runs per day, because they wanted to maximize how many different iterations and molecules they could simulate in order to make sure that they're optimizing and coming to market faster with their product. So you can see that there's a direct corollary, right? If you're cheaper and you're faster, then you're likely going to be able to run more per unit day. So the next workloads that we're going to talk a little bit about are LLMs. So I don't know if you guys are doing anything in LLMs and RAG models or like just generic open source models. We do a lot of work with Stability. I do a lot of work with other of the leading LLM companies in the world, but LLM really does depend on storage, right? So specifically for LLMs, what we find for some of the very, very like bleeding edge LLM providers is when they're doing dynamic modeling, right? So they're switching out models on the fly to make sure that they're consistently optimizing what they're putting out within their RAG workload. Model wait times are important. You need to basically eject all of your model from the GPU and then push a new model into memory in order to run your new model execution. And that time actually matters, and we'll get to that in a bit. It actually helps with simplifying embedding in vector databases. So embedding in vector databases are IO dependent. You typically will use some sort of NoSQL-like database in order to store that in. It optimizes for that and also optimizes for token retention. So when you look at like a RAG model, right, a generic RAG LLM, you're basically going to be collecting and cleaning data, you chunk it, you generate your embeddings, you store in a vector database, you implement a query, there's a semantic search that happens as a function of it, you extract, you re-rank variables, which determines your output, right? And then you generate, hey, this is the answer. Now, what I found, and this is just qualitative, not quantitative, right, is that each one of these different pieces uses a different type of IO profile associated with how it attacks, right? Like collecting and cleaning data, you're going to have a kind of similar IOP to bandwidth makeup. You're going to have a general file makeup, right? Because it could be some PowerPoints, could be some text, could be some images. Your read write, you're going to be a little bit heavier on the write, obviously, because you're doing writes in order to do that. And then your number of files are going to have more. But my point is that it's very variable across this entire process. What you also find is the counts of files and things like that really are important. So a lot of file systems don't handle small files and many files very well. You need to be able to handle all different types of scenarios, unless you specifically know I'm just doing this for video ingest. I know that my videos are going to be large, but I guarantee when you're doing your embeddings and things like that, you're going to have small IO offsets as a function of it. So cost optimizing and making sure you're using the right storage for the right job, again, is important. And that bleeds us into the mixed IO performance. So this right here is a screenshot from a very, very, very well-known LLM company, right? And what you'll find is a lot of times folks are like, hey, like, we're just really interested in throughput, right? You look at all of your NVIDIA benchmarks, all you need is how much throughput you can provide this P40 or P5D instance or this DGX system. What we find is that there's actually a ton of little small IOs that are making that up. That the large sequential reads that everybody's historically been good at, I say everybody, the Lusters of the world, the NetApps of the world, the Isilons of the world, any real type of cloud storage system that you would use, isn't necessarily the case.
Sorry, I don't want to give that question to the because only small audience. So this is come with a platform, or you have to build it yourself, like customer needs to build it.
So Weka provides this as a function of its storage system, but I'm talking generically across the entire like LLM RAG environment ecosystem, right? So you're going to have compute instances, you're going to have networking, you're going to have storage, right? Your networking kind of comes with your compute instances in AWS, GCP, and Azure and OCI, but you get what I'm saying. So all those pieces need to be put together from you, even though you're in the cloud, right? The cloud is great, it's a service-oriented world, but you still, if you're building something, are going to have to put these pieces together. My whole point about this is making sure that you're cost optimized, making sure that you're understanding what is your workload, what tool are you using, and I'm from a storage vendor, so I'm more specific around storage in order to make sure that you're optimizing your work.
So this for HANA dashboard
Mhm.
user can still customize it, right?
Yeah. This right here we put out is kind of an open source
Is that-
tool, like that's directly integrated with our APIs. And just pull that in, for sure. Yeah, so what we find is that the IOs are very small. We find that latency actually really matters, right? And if you take a look at the average IO size on reads, it's like somewhere around 300 to 400, not the 8 meg block sizes that everybody articulates within the cloud and within any type of storage presentation, right? And that you have a lot of small 32K IO. So my point is making sure you're aware of what are those IO patterns that you're seeing the most of. And again, making sure that your storage is cost optimized for it. So what did I do? I took a look at different types of small IO benchmarks compared to this again is Lustre because it's the leading like high performance file system within AWS. And lo and behold, better latency, right? Better read write mix for small IO really helped them out. And like this particular customer saw a difference. They saw 2.5x an increase in GPU utilization, which is huge. So GPU utilization is a whole nother talk track, right? Because I was talking with one customer and he's like, yeah, I'm fully saturated with my GPUs. I have X amount that I'm given, I have Y amount that are allocated. And I was like, okay, that's what's allocated from your scheduling system. But what about when you look into the actual, like SRAM, when you look into the actual NVIDIA commands and see what is the GPU utilization of this actual GPU, right? When you're sitting there and you're IO bound, you could say, yep, this particular application is using a GPU. It may only be using 20% of it because it's sitting there waiting for IO in order to serve it up, right? I'm taking a bunch of storage, I'm moving it, I'm putting it into the memory. That timeline actually matters. If you can iterate on that faster, lo and behold, your application runtime is going to drop, right? And that's going to be better cost. The interesting part about stability and what they actually did outside of increasing their GPU utilization, which if you're talking about 500, 600 GPUs within AWS, that's a significant cost value. They actually ran my products converged on their P40, P5P instances. So what that means is your P40 and P5P instances within the cloud, same thing in OCI, same thing with GCP, same thing with Azure, they typically come with network, they typically come with some CPU cores, they typically come with some disk, right? Local NVMe. We said, hey, instead of having a secondary file system that you're paying for, just take our software that sits in user space, it's in a container, we'll allocate the set amount of memory, CPU cores, what NICs you're using, we'll put it in that container and run our application right next to your GPU. And lo and behold, it happened faster. And lo and behold, it didn't affect GPU utilization. And lo and behold, now they don't need to pay for infrastructure for a secondary file system. All they're paying for is software costs. So you can really put together some interesting stories in how you can reduce cost over time and how you can increase your application performance. Again, just by changing the storage, which is crazy, but it's actually true. Next, we'll talk about some computer vision and imaging. So where you can enable GPU direct. That's the one thing I want to say. And in the cloud, it's kind of interesting because AWS and Azure don't have an RDMA enabled network. So you're kind of like stuck there. In that case, use POSIX instead of NFS, right? Use something that can parallelly push data to a single client versus a one-to-one because you're going to eventually be bottlenecked there. Or if you're in OCI, for example, there's RDMA enabled networks there. You can use GPU direct in those scenarios. It actually matters. And this is going to be an on-premise example of where GPU direct was and mattered. I'm going to abstract out some of the information, but it was for it's for brain imaging for people for children that need brain imaging for cancer related purposes and things like that. So it's a very well-known company. In general, they took a high performance microscope, and this is a super customized microscope, really great resolution, and basically it outputted around a terabyte raw image set of different slices of the brain. They wanted to piece that together and then process it. So they used the ZAR Python library. It basically enables you to take an image, break it up into multiple pieces, creates a file system structure from it, and it generates a lot of little files because you're able to specifically articulate various components based on the file system structure within it in order to process. So If you don't need to process this particular piece because it's not of interest to you, then you don't call that particular file, which means that you're going to save yourself GPU cycles. So that czar image format created around 50 million small files, and then that got sent to a GPU to process. In this scenario, I'll talk about two pieces that optimize this workflow. Number one is S3 and SMB. So you want something that's going to be performant. When you're taking a look at any workload that you're building, you're typically going to take data that's generated somewhere, you're going to move data into your environment, you're going to process that data, and then you're going to come out with an output. How you move that data into your environment actually matters. So in this scenario, they were using a system that was able to push SMB or S3 at around 3 gigabytes a second. At a terabyte image, it comes to around like 10.6 minutes. They were able to optimize that for SMB to do it a single vanilla Windows instance at 12.5 gigabytes a second. So now instead of taking 12 to 13 minutes to push that image over into their environment to process, it now takes 2.6 minutes. Benefit there is now you're going to be able to do 6x the amount of imaging and see 6x the amount of patients because you're going to be able to process it that much faster. Now, the GPU Direct stuff is completely different, right? So processing timelines for the images makes a lot of impact. You're basically taking all these tiny little chunks that you're creating with the czar library. You're then moving that into memory and you're processing that chunk. With NFS, they were doing it around 7 gigabytes a second, which is kind of standard. That would be very high performant within the cloud. We can do things that are really incredible in the cloud. With POSIX processing, they're able to get that done in 46 gigabytes a second, right? So now all of a sudden, you're 650% faster. Now I can see an immense more amount of patients process, get a result, and then help them on their way. And then with GPU Direct, it was an 1800% change. You were 1800% faster than legacy NFS, which is incredible to me, right? Think about how many more patients you're able to see. So where you can use GPU Direct, make sure that you're writing your applications that are CUDA framework enabled and can leverage those libraries because it does actually matter. And every customer that I know that's made that change has been very happy. Yes, for legacy applications that you have the code, it's been developed a long time. It's a lot of work to change that. You may not want to do that for legacy applications, just use POSIX. But if you're developing something that new, I highly recommend you take use of NVIDIA's tools because they're very useful. The other thing that they liked about the system is that its small file handling is very good. So what you'll find is S3, for example, is very poor in AWS with small files. You're not really supposed to write a lot of files under 32 KB, 16 KB. You're going to see space increase from it. You're just not going to see good performance at all. What they loved about this system is even within the cloud, right? We provide that NVMe cache that you're writing to and metadata writes to. Metadata will always stay there and then it moves down to S3. But when we move it down to S3, we'll chunk it together. So we're basically able to handle small files really nicely. So they were able to handle like the 50 million small files and do an LS on them incredibly quick. I think it was somewhere around like 6 minutes for an LS of 50 million files, which is incredible. I did this bottom one. We did it for an automotive manufacturer that is the leading automotive manufacturer for computer vision, right? They're the ones that have like all the cars out there, right? Their telemetry is incredible. They're doing billions of small files within their telemetry. Everything that car is producing is being outputted in. There is some differentials that's being developed, right? Because you eventually have a bandwidth constraint when going over Wi-Fi, but or generic WAN. But in general, right, you're able to run 1 billion files doing LS in 4 hours. I've never seen a file system be able to return a value in that time, right? Like it always would just wait forever and I kill it after 7 days. So, I'm gonna kind of end it because I'm right at time. But Weka in general, for those of you that are interested, I work for Weka, and this is just my quick plug. We're a file system that can be deployed in hyperscalers and GCP cloud marketplace and GPU cloud marketplaces, on premise with whatever you want, or if you have a SuperPod, we can use this for SuperPod storage as well. As I pointed out, we can do Ethernet or InfiniBands. We can do them both at the same time. This is showing a little bit of thing with Dell, but it can be any x86 server. We deploy on any x86 server. So it could be Supermicro, Lenovo, HP, doesn't matter to us, right? In general, all we need is an x86 proc, some TLC memory, and some network NICs. Or in AWS, we typically deploy in i3 EN instances. We deploy in LS instances within Azure. We deploy in bare metal within OCI. And then that attaches to an S3 object store. Then you can cost effectively scale your file system in one single namespace, read it where you wrote it mentality. We'll modify where objects live, so you don't have to, and you can scale that out to the exabyte range. And it can also be snapshotted and deployed in any major public cloud. So if you want to have a dual public cloud strategy because you're worried about GPU availability, well, guess what? You can use Weka, same exact Weka bits in GCP as you can in AWS, as you can in OCI, as you can in GCP. So it creates a lot of like synergies there for your application stack. And that's it. Thank you guys. I appreciate your time.
So Ben, we have some time, so if you want to go back to the small file.
Yeah.
So is that automatically, like, do you put small files together automatically or?
Yeah, so that is one of the benefits. So I used to be a big Lustre user, and I used to hate the fact that I have to go and literally like create a file system based on what's the IO profile. How many files am I gonna have in there? What is the interaction? With Weka, it's a massive parallel file system where everything is on the same server. So you converge metadata and data all on the same thing. So we can handle billions of small files up to, I think it's around 7 trillion without any administration change. You just bring the system up, create one of thousands of file systems so you can multi-tenant it, and you can handle all these files without any problems.
Let's do a very specific example.
Yeah.
I have existing file system in HDFS, for example.
Oh, I know HDFS as well.
Millions of millions of files. I upload it to your file system.
Yep.
Would all my files be combined automatically or?
No,
What needs to be done?
So what would happen is you would move your file systems from HDFS, and you're probably addressing it over HDFS or S3A, right?
HDFS is horrible in small files.
Oh, it's terrible because you triplicate or
Yeah.
5x.
All of
create-
them
because
in
no one-
cost just kills the job's performance, so.
Yeah, so we would definitely be able to help in that
Yeah.
scenario. So our small file performance, I would, when 100 gig client, I'm able to push out to a single client at around 7 gigabytes a second of 4K files. So our small file performance is absolutely
Oh, so it's,
incredible.
that your system works better for small files,
Right,
it's not like,
It works better for small files, and when you attach an object store to it, which is more about like cost effectiveness, here, I'll get to this point, which is more about cost effectiveness. So when you attach the object store, we'll basically take those files, metadata remains in NVMe, and then we'll chunk them up into 64 meg objects, because S3 doesn't really handle small things well.
Yep.
And then we'll dump it in there, but when we address it, we'll adjust the byte range within the object, so we're able to pull back.
so you
just
do a
the byte
search
range.
and find where's the file and just.
It's a couple key value pair combinations, and you're able to push it in, but your initial small file access would be on the NVMe and really fast, like I pointed out. And then as it bleeds down based on access time over X period, because you don't want to put everything on NVMe, it's just crazy cost. Metadata remains in here, so your metadata lookups are quick, and then it'll go and byte range tree and pull back.
So it's called WCAFS.
Yep.
And it supports any like file protocol, like, or is it-
Yeah, so we support S3, SMB, NFS, POSIX, and then CSI, and then GPU. So more than happy to give a deep dive if you want. Like, I tried to make this more like scientific focus because it's an IEEE, right? Not necessarily a product pitch. 'Cause-
But yeah, but also a lot of companies, people, so. At least myself is,
Yeah.
finding this interesting. Yeah, so the whole system, is a file system, is it your file system, you know,
Yeah.
specialized in file system?
Yeah, so here. Here, let me show you.
But I missed the beginning, so.
Let me see if I have something up. No, that's not gonna work. That's a loop back to myself. Oh, 7. Okay, cool. So I got a file system up 172.29.07.
It's on meeting?
Yeah.
Okay, maybe, yeah.
Here, I can close it if you want.
Yeah.
Here we go. Yeah, I will leave this.